So this is more of a fun talk, but I also hope that by the end of this, you will have something that I guess today is Friday, but maybe on Monday, you can actually put into some actual real code bases. This is something that you should be able to take away and start using immediately. This is not some kind of highfalutin concepts. This is actually real stuff. So as a result, what we're going to do is we're going to explore scalameta. We're going to come up with some motivation for why we even want to do this in the first place, what scalameta is. We're going to use kind of a straw man of building case classes from scratch. We're going to start with a base case class. We're going to extend it with some methods. We're going to add some kind of JSON deserialization stuff to that because people like that. And then additionally, I guess this is more relevant here even than back home. Let's talk about what real world code generation means as far as something like GDPR. So let's say you have a big, somehow remarkably comprehensive a law that requires that you have a really aggressive data redaction, and you don't have a lot of guarantees about your code base. How can you ensure that you're not accidentally two-stringing something in a log somewhere? Turns out, if you don't rely on the built-in two-string methods of case classes, you can solve this problem very easily. So that's what we are going to try to cover today. So the thing that I'd like to show first is actually just that scalameta is a library, like any other Scala library. It is available under the org.scalameta organization. The artifact is just scalameta. You pull the latest version, and what you get is this. That is not what you get. You get this. You don't get that either. Let's go to, sorry. Because, yeah, exactly. I have to reload in both projects because, here we go. So what you get is quasi-quotes. You can define something, let's say, foo is 5. This looks like Scala, tastes like Scala, is Scala. But you can also see the actual AST of the underlying stuff. And this explodes to the entire Scala file. You can copy and paste entire source code files into these quasi-quotes, especially with triple quotes, and you can have the entire source tree of a Scala program represented in its AST. What's even more remarkable, I would say, and actually my favorite party trick, I'm great at parties, is you bind something, and then you swap it around, and doesn't that look cool? It didn't do anything because I actually didn't do name or, nope, the up arrow is over here. Body. Typing at this angle is challenging. You have to be patient with me. Name and body, right? So this is actually completely unpack all of this stuff, round tripping through real values. This quasi-quote stuff is really remarkable. So we're going to use this in this talk to do something that not only is tractable and approachable. Sorry, folks, we're still looking at that. We're not going to just do something that's approachable, but also we're going to use this to great effect, right? So we want to get something pretty significant out of it. Additionally, because this is some real world stuff, I want to be able to put this code generation into an existing SBT project. If you're using Mill, if you're using Maven, doesn't really matter, hook it into the right place in the build phase. And the main thing is your code generator is a bit of code that will emit a Java file path that can be picked up by the compiler. Doesn't matter how that happens. You put it in a magic file, magic directory somewhere, totally fine. We need a little bit of kind of goo in SBT to make this functional, or to make it not functional so much as work, but overloaded terminology there. What we're going to do is we're actually going to just look at what that means in SBT. The write files function here is a function that takes a scalameta source as well as a target file path. And it will just emit a list of those file paths, and very straightforwardly just maps over, creates the directories if necessary, it gets uses, I'm going to switch to the other screen again, because this, we saw structure earlier. This shows the structure. It's actually syntax as well, which shows the actual Scala syntax. Scala Meta also has dialects. So if you want to use Scala 3 syntax, you can actually import the Scala 3 dialect and you can have real Scala 3 code, which is also pretty neat. They've done a really good job with this library. You should use it. The last part here, generate task. This is just an SBT task. The reason I've defined it as a separate thing from write files is because the write files is the generic stuff you can put at any build tool. Regenerate task is the thing that you need in SBT. And that's what's actually extracting the compile source managed, as well as calling emit sources and then calling write files. Emit sources is actually I forgot to mention earlier, up here, emit sources is where we're going to be putting all of our dynamic generation stuff. Here I have an empty list as an initial, but we're going to fill that in as we go. So given that, we saw a little bit about how we can destructure simple methods, but this, as I mentioned, also scales up to entire classes. The structural decomposition here is something that you're going to be thinking about as far as how you model this in your mind. You're thinking about the underlying nature of the thing that is being described. In this case, it's the class and the toString method, decomposing the foo bracket and all of the pluses in between. If you want to use string builder, fine, that's also acceptable. This is a short talk, so it's not that important that I do so. But if you want to do more efficient stuff, you can. The most important thing is that because this is, again, Scala Meta, this is just a function, I can actually just define a build pojo method, which actually exposes this class with the build toString method inside of it, but it's almost like string interpolation. So I'm going to lean heavily on this. A point that I'd like to point out is that because we very often use the same term, the same name, the symbol, in the type level as well as the term level, Scala Meta actually maintains both of these as separate concepts. So you'll actually see the same value here for class name being bound both into a term as well as a type and used in different places. You can see the class is a type name because that's apparently in type scope, but you'll also find that I don't think it's here yet. We're going to use it in the companion object because the companion object is a value. So we use that as a term. So the type level types are types, and the terms are things that you can actually call methods on and whatnot. So that's a distinction you'll see. The actual toString method generation is something that looks maybe a little bit hairy, but the thing that I'd like to point out is, as we saw in the console, if I have a list of parameters, it doesn't really matter what the parameters are. Let's just pretend that the case class has a bunch of parameters and they all have names and types. The thing that we can do with Scala Meta is we can iterate over all of those parameters. We can extract the name. We can ignore the type because we don't really care what the type is. We can take the name as a string. We can concatenate that with an equal sign. And then we can just call the underlying term.toString. So that's all here on that line there. And we want to also be able to, pretty print this and make it look nice. We can do that by way of folding left over all of those. If we have seen, if we've seen a term before, then we can interpolate a comma. But importantly, we can't use makestring because we are not running Scala. We are running Scala Meta. So we can't actually toString these things. We can't makestring these things because we're trying to macro generate the code that is then going to be compiled. So if we tried to use makestring here with a comma as the argument, we would of course get not what we want. We would get the compile time representations of the AST nodes. We'd get the names in Scala, not the actual functional stuff that works. So we just combine that all together. And the result here is this override toString. The return type of this function is a def and def. This is the defin is the companion object for various definitions. A def is just a function. So because the result there is just a function, when we call this method up here, build toString, that's actually returning an actual definition that goes right into the middle of your class. And suddenly your class has a toString. You can pretend as though you wrote it yourself. You can use this to generate instances of the various like functor instances of something like that for tuples, or you write all kinds of really abstract, cool, fun stuff. But all it boils down to is if you can think of how to destructure your actual code into its constituent components, you can actually co-generate this. So given that, we can also look at what it means to make an apply method. An apply method on a companion object is very straightforward in the same way as our toString. All I want to do is I want to iterate over the parameters instead of, in this case, ignoring the type of that thing, the type of the parameter. Sorry, we're going to ignore the type here as well. We're going to use the type in the JSON decoders that's coming up soon. I'm actually going to use the entire parameter list in whole as the argument list to apply. So the exact same arguments that are valid for my case class or for my Pojo class are also valid as arguments to apply. The type name that gets returned is the type of the class. And the assigned parameters here is actually just destructuring the parameters, taking the name of the term and setting name equal to name, so that I'm doing the name, like the name-based assignment of each of the parameters, just in case things get screwy. You can still say, all right, at the very least, there's consistency there, so there's no ordering problems. This works quite well. We can actually see here, I forgot to run the last example, but we'll run this one. The last one, I did a print line with new and foo, and this time we can actually see the same thing. We are going to see not only the toString, but also the fact that I can call the companion object's apply method. So one other thing is that because we're doing this development of this code generation plugin in SBT itself, what's nice is that we don't have to publish jars every time, because it's actually, the definition is in the project. But we do have to reload SBT because the definition of all of this is one level up in the project hierarchy, right? So you can actually define a project /src/main/Scala, and if you put stuff in there that then is used by your main project definition, you can generate a bespoke Scala SBT plugin that generates code as you go. Also, if there's any questions about any of this stuff, feel free to shout them out, or we'll get the microphone. But let's see whether or not this works. Let's go back and look at the main here. We should see foo 1, 2. Sure enough, foo A equals 1, B equals 2. Because we did the nice pretty printing, we had the labels in there as well. And this is real code, and we can look at that as well if we pop this open, target source managed, nope, target Scala source managed foo. We can actually look at the generated code as well. This is not macros in your, this is not your granddad's macros or whatever the meme is. This is actual real files living in the file system, and you can inspect them. You can add this to your IntelliJ source path, and it will just give you pleasant and nice navigation to all the different definitions of all these classes without any sort of macro reflection by developer integration tools. So the tools are great, but at the same time, I want to be able to see the file. I want to be able to hold it. And if I need to, I want to be able to disable the plugin and move the generated file into my code base to modify it if necessary. Let's say that there's some sort of massive fire and it's 3 in the morning and I have to put it out. So speaking a little bit from experience there. Additionally, you would want something like copy. Copy is fairly straightforward. You want to set each of the parameters equal to this dot, it's the name of the term, and then just return the exact same thing. So we can look at the definition for this as well. As we are building the copy, we accumulate from the parameters list. We will iterate over each of the parameters. We'll destructure the term. We will bind the term.name as term, and then we can just create a new param on this line here with the param $term :type. That's what gives you the beginning of the term type, and then the equals and this dot term. If you read the line, it looks very similar to normal Scala, except with a bunch of $signs in there. This is intentional, I think, and I think again, this technique scales very, very large. Maintaining a code base that actually uses this stuff. You may have seen the talk yesterday about Guardrail. The entire internals of Guardrail is using this. Scalameta has been basically the only way that I could maintain a project that large, because internally it has assertions of what things are valid syntax in Scala, what things are valid constructs in Scala. If you try to do something that is nonsense, then the actual library will complain. You've tried to construct something that's impossible, like for instance, trying to there was actually one of these things where for comprehension has to have at least one bind. So if you try to pass an empty list into a for comprehension, it will explode. I would love to know that at runtime of this compiler, or of this library rather, but instead of once I generate the source code, the compiler plugin's like, oh, everything's fine, and then turns out that your source code is invalid. I want to know that before. So sure enough, we have some basic assertions. You can still do things like I'll actually point out here. This is not typed. So if I do this, this will, of course, compile and be nonsense at the same time. Specifically, it doesn't know about anything. This is just the structural syntax of Scala. So don't expect it to be typed in terms of the representation of the AST, but the structure is typed. So the structural representation of the AST itself it has this representation that has some assertions that are built in. And we can actually see here in the main.scala, if we reload and run, we should expect to see the 2 has been replaced with 2. Sure enough, it works. So let's move along here. Automatic JSON decoders. JSON decoders are a super fun hobby. Everybody should write one. The thing that is important about this is that I don't want to write them anymore, and I don't want to write them for every single one of my classes. I also don't want to trust dynamic derivation of these things that just kind of imagine what the thing should look like and then make up something that's really cool but also very wrong. So I'd like to have some sort of guarantees of the derivation, and the way to do that is of course by coming up with a set of rules that you both own and can understand, but also that automate the pain points of your workflow. This is, again, the point of this talk is this stuff is usable today. This has been available as a tool, but it's not as accessible because there's some sort of confusion between macro generation and just source code generation. So this is specifically trying to disambiguate that, and this is the purpose of this talk. So if we walk over all of the pairs, we use the enumerator.generator here to do the term arrow expression to do those bindings. We do one of those bindings per each of the elements in the parameter, and inside there we get the value out of, let's say, a JSON object. We use .get. We get it by name here. We're not doing any sort of name rewrites, but that's something you could do there. We pull out the JSON decoder for the type that is specified, and then we use that from JSON in the flat map in order to do that decoding. The expectation here is that the decoder here is using option as its return type. Obviously, this is not the one that you would want to use in production because it hides errors, but it's, for example here, that it's good enough. There are ways to do this in a more robust way, but it would take more of a slide. So given that, we accumulate this set of generators as well as the term equals term. So because we also do want to assign that in the constructor of the object, what we end up doing is this, we accumulate this pair of the generator as well as the term assignment. We do have to do that pair's length is greater than 0 to ensure that we don't have an empty for comprehension. But once we do, we can actually look at the JSON decoder here. This is the implicit instance of the JSON decoder. And I should also mention this is just a toy JSON decoder that I wrote in this project. So this entire project, other than the scalameta dependency, is entirely self-contained. You can pull down the slides and you can run them yourself. If we are trying to decode a JSON object with a value, then we throw all the code that we just wrote for this for comprehension, we throw it there in the body. Otherwise, it's not valid JSON in this example. So the thing that we do here is we actually, in the main, we construct a JSON object, we pass in a map, we construct all of the parameters, and then we try immediately to decode that from JSON, and we should see what that looks like now. Sure enough, round tripping from JSON, well, going through JSON, not round tripping, does work. So that's great as well. The nice thing about having done all of this in a very abstract way is we can add more of these definitions. I did forget, I think very early in the talk, I forgot to call out the build.spt where the bespoke plugin.spt, where we defined this emit sources earlier, and this was initially just an empty list, but we did add this build pojo foo with all of the parameters. So if you were wondering where the parameters were and how it knew to generate foo.scala, I do apologize. That's where all of that was happening. We can see that this actually scales because we can have bar and baz as well. We can put them in the correct files. We're managing the file path here ourselves, but if we needed to, we could come up with some way to abstract that as well. But yeah, I think Alexander's talk earlier has pointed out the follies of too many abstractions. So let's just stay with the one. We have this foo, this bar, and this baz. We should be able to reload at this point, and let's look at target Scala source managed main foo.scala. So let's confirm that when we run this, well, actually won't even run it at this point, just compile, we should actually see the other files appear in there. If we look at bar, we should see not only is the class there, the companions there, but also the JSON decoder. I didn't have to touch bar, I just created it, and magically it had all that stuff in it, which is pretty nice. And then baz has the stubbed JSON object because it doesn't have any parameters. So if you try to decode it from JSON, then it is successful every time. So given that, we can also look at what it means to add additional parameters to things, because we're modifying our business domain as we're evolving our company. We're trying to solve new hard problems. Adding longs to case classes is very important for this need. So as a result, we are just going to modify foo to also have another parameter c. So we reload this, we run this, and sure enough, we actually see the C. So there's a C there now. And then we can also talk about field redaction. This is the big domain modeling GDPR thing that definitely was handled completely correctly by every single company on the planet recently, well within the past 10 years, and definitely did not burn hundreds and hundreds and hundreds of hours. Here we're doing it in about a minute and a half. Because we have control of our toString, we can just take our list of redacted fields. We can check to see whether or not the term's name. We cannot just reflect on the term. We have to actually access the underlying string of the. We can look at whether or not that's in the redacted fields list. If so, replace it with some asterisks. If not, then just use it as it is. This isn't recursive. So if you do have secrets that are inside other things, actually it is recursive, because if you have secrets within those things, then it delegates to those toStrings. So it is actually, it should just work. So given that, we use the new lit string with the field equals and this new interpolated value. We can reload here as well. We can run. Sure enough, B has been redacted. So no one will ever have to see the word to again. Given that, we have reached the end of the talk. So this is where I will accept questions, and I really hope that you use some of this stuff. So thank you.